Okay, welcome to the Retinanet tutorial. In this tutorial, we'll be going over how to train an object detector completely from scratch on your own dataset. So we'll be going over how to grab the data, how to format that for Pascal VOC that Retinanet can use, how to actually train the network, and then a quick demonstration of what the network can do. This tutorial will make use of Keras and TensorFlow and also TensorBoard. It's based on the excellent implementation of Keras Retinanet by Pfizer, which you should definitely read if you do have the time. This tutorial is mostly aimed at people who want to get something working extremely quickly and don't necessarily care about all of the details behind it, and also at anyone who is interested in using their own dataset. In our case, we'll be training an example detector on red plums, which look like this. This is just some data that I had lying around that I've been using recently. So we're going to use that for training an example detector. Okay, a quick note on ROS. ROS is the robot operating system. If you've never heard of it, feel free to skip over this bit. However, I've been using ROS to extract and to manage the data that we're using for training. So these plum images have come from a ROS pipeline that's been used to read sensor data off a camera. There is also a ROS node included down here. If you read the Using ROS README, that will go through how to use that ROS node if you want to implement a detector in inference mode running as a ROS node. So let's get into it. The first step is installation, which is always hard with any sort of deep learning framework. You will need the NVIDIA drivers if you're using an NVIDIA GPU, which I recommend you do because it is extremely slow on CPUs. You will also need CUDA and CUDNN to go with that. You want CUDA version 10.0. You will also need TensorFlow, Keras, and a bunch of Python libraries that will be installed automatically. So there are some instructions on installing drivers and CUDA and CUDNN here. I won't go through them in the video. To install TensorFlow, you want TensorFlow 1, and you can install it with that command. If you don't have a GPU, the package name is just TensorFlow. We're using the original version of Keras, not the TensorFlow implementation of it. So you just want Keras, not TensorFlow Keras. During this tutorial, we'll make use of 3 different repositories. This one, obviously, which has a few things we need in it, so you will have to download that. The Keras Retinanet implementation, which is that one, and we'll be using the label image tool as well. So to begin with, we'll start by making a directory under the home directory, and we'll start cloning some of these tools into that. So first we'll get this one, then the Retinanet one, and finally label image. Label image is quite large, so while that is downloading on my very slow connection, we'll go through how to start creating the dataset. So we're going to be starting from, if we open up the folder we've just created, this is the tutorial folder we've downloaded, and there's a folder called raw data in there. Under this folder are 60 images taken directly from a camera feed at regular intervals. The first step we want to do is cut this down to around about 15 images. 15 is a very small number for a deep learning dataset, so is 60 in fact. Many of the large data sets have images in the millions, so we don't expect to get very good results from what we're going to do today. However, even with a very small number of images, we should get a detector that works, and we can certainly demonstrate the training process using a small number of images. When we create our dataset, it's important to pick which format you want to use. So the Retinanet-Keras implementation has 3 available by default. The first of these is Pascal VOC, which is the format we're going to use. You can also use the Cocoa format and this CSV format that they've constructed. The CSV format is probably the easiest format to create. However, we're going to be working with Pascal VOC because it is a standard format. So if you switch to a different network, you can take your data with you and it should all just work. In order to create this Pascal VOC dataset, there are 3 folders. The JPEG images folder, which has the JPEG images in it. The annotations folder, which has an XML file for each one of those images. And this image sets main folder, which has text files that list some of the different data. The first thing we're going to do is create the JPEG images folder. So we're starting with this raw data folder, and we want to cull it down to around 15 images. The first thing we're going to do is make a new directory under our tutorial folder called data. We'll select 15 of the images from raw data and copy these into data. These are the images that we're going to label. So when we're selecting these, we're looking for images that are going to be easy to label. Something like that is obviously going to be quite hard. There's a lot of examples in it. That's not necessarily a bad thing, but it will make labeling harder. You want ones that are not too blurry and images that actually have targets in them, so that one's no good. So let's select 15 of these. We do want to try and make them diverse, so there's no point labeling the same image over and over. It's not going to give us many benefits when we're training. But we'll get some of these ones. So 11. Okay, that's 15. We will copy these into our data folder that we've created. So you'll notice in this folder, each of the file names is not necessarily in order, and they don't mean very much. This left actually means it's coming from the left camera of a robot, but that's not very useful for us. So what we're going to do is batch rename these, and you can do that using a tool called Thuna, which you can install with that command. I already have it installed, so what we want to do is change to the directory that has our images in it. We will run Thuna, which is just a file manager really. It's like Nautilus, but it has this neat command where if we select everything with Control A and then go to rename, it allows us to easily batch rename files. We want to select the number format. We'll start at 1. We'll prepend this batch1 text to it, so we've got text and then number, which gives us a file that looks like this, the file name. The reason we add this batch at the start is if we go back and train more data in future, then we can give it a different batch number, which allows us to track the data sets very easily. And if we simply copy the images and annotations in, they won't override any existing files that happen to have the same name. So that's why it's good to rename them in batches and numerically. So if we hit rename, those are now batch 1 through 15. And we are very nearly done with the JPEG images folder part of our dataset. So the next task is to actually set up the 3 different folders within this Plums VOC dataset that we're about to create. So we're going to make those directories. And then we will copy everything from Retinanet tutorial data into Plum's VOC JPEG images. This Plum's VOC is now the top of our dataset. That's the top folder. Okay, so now we're on to the labeling step. We have created this Plum's VOC folder. It has our 3 key folders in it. JPEG images is done. They're all in there. The next step is to create the XML files within this annotations directory. So we're going to change to the label image tool. We do actually need to build that, and I'm going to use PyQt5. If you do get any issues when you're running either this line, the install line, or the make line, then I suggest you use the virtual environment instead. The instructions for using the virtual environment you can find just there. So that's if you have any issues with installing it. So you just need to make that, and then we can run it. So this is our label image tool. Before you go ahead and start labeling your images, the first thing you need to make sure is that this autosave mode box is checked. So make sure that box is checked. Then click Open Directory, and we need to point it to the tutorial Plum's JPEG images directory. We need to set the save directory to the Plum's annotations folder. That's where our XML files will be generated. You should check that this is Pascal VOC and not YOLO. And we want to set a default label, which we are going to call Red Plum. Now, if we click the Create box, we can start to label our data. The W key will bring up a new annotation box. And you just want to create boxes around each one of your to-be detected objects. If you do mess up a box, you can drag and resize them. You can also select them over here and delete them. You are able to zoom with Control Scroll. One thing we want to do is to create a second class, which we'll call Green Plum. So we just change the default label, and we're going to label just a handful of these as green plums to demonstrate multiple class training, even though they are definitely red. Now that we've got 2 green plums labeled, we'll swap back to the red label, and we'll go through and label all of our data. This usually takes me around 10 minutes to do for about 15 to 20 images, depending on how many are in the actual images. While there are a lot of good labeling services which are extremely cheap, I would recommend labeling at least some of your own data because it will highlight issues in the data that you otherwise wouldn't see. You get a much better understanding of what's there. So if we've finished this image and we hit the next image button, it will create in that annotations folder an XML file which has the same name as our first JPEG image. So batch 1, number 1. If we open that up and have a look at it, you can see it's encoding the path to the image that it's annotating. Some basic information about the image. It's an RGB image, so it has 3 colors. 3 channels rather on the final dimension. And you can also see that it has this truncated and difficult tag. The difficult tag you can ignore. The truncated one will be set to 1 wherever the bounding box intersects the edge of the screen. So this one should be labeled as truncated. It may not be because it's not quite at the edge there. So that will now be a truncated label. that is pretty much it for the XML format. The only next step is to go through and label all of the data. So I'll just do that quickly now. We only have 15 images, so it shouldn't take too long. Okay, we're now done with labeling data. So we need to hit the save command on the very last image, otherwise the last image won't save. And we can check that we now have 15 XML files in our annotations folder, and we do, so that's good. The next step is to make this image sets folder. It's actually two folders, image sets, which has nothing but main in it, and then within main we need three files: trainval.txt, train, and val. Trainval.txt has a list of all the files we're using in our dataset. Train and val are the split between train and validation, and these files are just going to have the file names in them. We've already done that line. Rather, we need to run that to change to that directory that we've already created. And then we can run this command to generate trainval.txt. If we open this, we see we've got everything we need, the list of files. The only thing we need to do is get rid of these file extensions because they're not meant to be there. We can do that with the sed tool, which is finding all of the .jpeg text strings within trainval and replacing them with nothing. We now need to create an empty validation text file, and we want to create the train file from a copy of trainval. So we now have our three text files. We want to open train and val. We're going to manually move some of these from the train set into the validation set. Typically you want around 60% of your data in train and around 40% in val. If you've got a really large data set, you would need to automate this step of randomly selecting some and moving them from train to val. For this very small data set, we can just cut and paste them. It's important that the validation images are not in the training set. So now we are actually done with the dataset. Our plums VOC dataset is completely set up and ready to go. We've got the images, the annotations, and our train validation split. The next step is to actually set up the some directories that we're going to use for the training data output, and then to set up the Retinanet network itself for training. We're going to make this snapshots directory where the model snapshots are going to go. So these training output.snapshots, this folder is going to contain all of the weights snapshots of the network as it trains. So for each validation step, we're going to get a snapshots weight file appear here. There is one file that we need to edit, which is under Preprocessing Pascal VOC. This is what's called a generator file for this dataset, which generates the training data that the network actually needs from the correctly formatted Pascal VOC folder. However, in the original Pascal VOC dataset, the list of classes looks like this. None of these are plums, so we need to go ahead and modify these lines to look like this. We have a red plum and a green plum. If you only had a single class, it would look like that. make sure to not forget about the comma there. You do need to remove that on the last line. So we'll save that. If you do want to use it with the Pascal VOC model, so the pre-trained on Pascal model, you would need to leave all the original classes in there. So you should maybe make a copy of Pascal VOC if you want to use that in future with a Pascal VOC trained model. We're done with that file, and that's the last change we need to make to that. So we're now ready to build Keras Retinanet, and then we can start training. So we're going to change to that folder, which we're already in. Yep. If you don't have NumPy, we're going to install it now. If you don't have NumPy, you probably don't have a bunch of other stuff that you've already run into issues with, so you should have installed all the dependencies already. We're going to install it into as a user install, but we are actually installing it, not just running it from the directory that it's in. And the reason for that is our test detector.py script, which is in this repository, needs to be able to find Keras Retinanet. So if you don't want to install it, you don't have to, but you do need to make sure that test detector.py can find it. We're going to install it now. We're also going to build the local copy in place so that we can use that to train the network. You will likely get some warnings here. That's fine as long as it builds. We're now almost ready to run the training command, but let's just break this down a little bit so you know what's going on here. So we're running Keras Retinanet bin train.py, which is the main training file. We're going to pass it a TensorBoard directory so that it writes TensorBoard event files into training output. That way we can watch the network graphically as it trains. We're passing in a snapshot path so that it knows to save the snapshots to the snapshots folder. We're going to make sure random transform is turned on. So this will do some random augmentations to our data to make our tiny little data set perform just a little bit better. So we're going to make sure that's turned on. We've set the steps to 100 for this training example so that you can see the validation loss drop, and because our data set is extremely small. The default steps value is 10,000, I think. So if you've got a normal size data set, steps should be somewhere between maybe 2 and 10,000. By setting the steps very low, one other thing happens. You will get a lot more TensorBoard events files coming out, so you'll be able to see the training occurring a lot better, but you'll also get a lot more snapshots. And each of these snapshots is around 0.5 GB. So they can very rapidly fill up your hard drive if you don't keep an eye on them. What that means is if you run a long training session, you may need to either increase this steps value or delete some of the older snapshots files as they start to fill up. The final argument is we're going to use the Pascal format dataset, and we're going to point it to this plums VOC folder that we made. So now we'll hit enter and hope that starts to work. One thing you should do after it's printed out this model summary is scroll back up to the top and go through and flick through some of these outputs to make sure you haven't gotten any warnings about CUDA libraries or CUDNN libraries that were unable to be loaded. Because if you do get those warnings, they'll still show up as normal, but it means it's running on your CPU instead of your GPU. One thing we can do to check that is run the NVIDIA SMI command. What you're looking for is that your memory on your GPU should be mostly used up. You can see this Python training process that we just started is using about 90% of my GPU memory. So that's good. It's running on the GPU and not the CPU. So if we scroll back to our training output, you can see it's almost finished the first epoch. Once that hits 100 training examples, that means it's gone through 100 batches, I believe, rather than images. And it's then going to run a validation step. So it's run that validation step, which means it's written out. It's actually run 2 now. So it's run 2 validation steps. Each of those validation steps has this .h5 file, which is the snapshot of the model weight at that validation step. And it's also written it into an events, a TF events file that we can read with TensorBoard. So let's go ahead and start that up. We'll open a new tab and run TensorBoard, pointing it to our training output directory. Then we want to open that link in a browser, and it should look something like this. So we've already got 3 checkpoints written to that TF events file, and we can see the loss from those in this graph here. You can also look at the classification loss and regression loss separately, but the overall loss is the most important value here. So if we make that a little bit bigger, we can hover over it, mouse over it, and see that the value is actually dropping, and that's what we want. One thing to note is that this TensorBoard loss is indexed from 0, whereas our snapshot files are indexed from 1. So there is an off by 1 thing, where if you wanted to grab step 2, that's actually going to be Pascal 03. So that's now training. What you want to do is 2 things. One, keep an eye on the disk usage of that snapshots folder, because it will get quite large. And the other thing is to watch the TensorBoard loss. So this curve will drop quite quickly, and then you'll see it start to flatten out. And as it starts to flatten out, you want to watch where it stops improving, and then grab your most successful model file from where the loss is lowest, but before it has been flat for a long time. So we're going to let that run until the validation loss flattens right out. Okay, that has almost finished training, so we're going to stop it there. If we let it train for another maybe 10 to 20 epochs, it would probably get a little bit better, but this is good enough for our demonstration. So we're going to stop at training. We're going to grab the model corresponding to step 34. We'll just Control-C that. We can delete all of these except for 35, which is the last one we saw on TensorBoard. We can go ahead and close TensorBoard as well. We're done with that. What we're going to do here is create a Retinanet models folder. We're going to move that .h weights file into that folder. This is our trained model now. The one thing we need to do, which is special, is actually convert it from a training model to an inference model. There's 2 different types of models. The inference model, obviously, you use for inferencing, but you can't use for training and vice versa. So we're going to make that directory. We're going to copy the snapshot that we want. In the text, it's number 6. In our case, it's number 35. We're going to copy it into that folder, and we'll call it plums training. Then we change back to the Retinanet folder, and we run this command here. What this will do is convert our model from a training model into an inference model. It's worth noting that it's looking for this plumstraining.h5, which is the one we just moved in, which is why it needs to be called that. Okay, that's now finished. We have our inference.h5 model, which you can see is a lot smaller than the training model. If you did want to use your training model to fine-tune it on additional training or more data, what you could do when running the training command is add the snapshot argument. I'll just get rid of all this so you can see what all of the options are. So there is this snapshot, which is different to snapshot path. That's the one we used before. If you add a snapshot argument and point it to this plums training file, it will start training from that snapshot file. There's a few other options in here. We've gone through most of them. You can read the documentation on those if you want to use any of them. But that's how you do training from a checkpoint. Okay, so the final thing we're going to do is test our newly trained detector using this testDetector.py script. So you can find that in the Retinanet tutorial folder, testDetector.py. If we open this up, you'll see that there are 3 paths near the top that you will actually need to set. So you will need to change that to be your username, and then the rest of it should be correct. It's going to load this plums inference model, and it's going to apply it to this plums test image, which is this one. And then the output is going to be saved as plums test underscore detected, which is that image there. So if we run that test detector script, you'll see it creates a TensorFlow session, it loads up our model, it runs inference on that image, and then it saves the output of that image just here. So you can see that our model, with only 15 training images, did actually work relatively well, surprisingly well for such a small amount of data. If you wanted to improve the accuracy of that, the first step would be to label and train on a much larger dataset. That pretty much concludes our tutorial. If you do want to look at implementing this in a pipeline of some sort, have a look at the using ROS stuff, and also have a read through the FAQ if you're interested in building your own dataset, which is really the sort of point of this tutorial. Hope that's been helpful, and enjoy your work.